Welcome back, everybody. So the timing was perfect for syncing the break with the start of a new module. So now we are going to be looking into Spark. Spark is the next generation of MapReduce. So I'm going to explain to you now what the developments have been. So the idea of having a job tracker and a task tracker is actually the first version of MapReduce, probably 15 or 20 years ago. But since then, there have been engineering improvements that I would like to tell you about, that you see what has been done to improve it. So I'll start with that, and that will bring us to Spark. So you see we are here on the processing layer. We've done everything that's below we've already covered, and now we are in the processing part. So you saw that in MapReduce, it's basically a very simple model where you have a map phase and a reduce phase separated by the spaghetti in the middle, the shuffle phase. We saw how it can be executed in parallel on a cluster on slots with within each slot sequences of tasks. We saw that in version 1 of MapReduce, the early version, we had a process called the job tracker co-located with the name node process, and the process called the task tracker co-located with the data node processes. And the idea is that the execution on the task trackers of the map functions should be on the same machine as the blocks that they are reading from disk, because then you can short circuit the HDFS and directly read as a local read. This is what we call bring the query to the data. Now there's a couple of problems with that design. And one of the problems is that the job tracker is doing too much. It's taking care of the resource management, so managing all of the available machines on the network and knowing which ones are available. It's taking care of scheduling, so it has to figure out whenever a slot is done, what tasks can they do next, depending on whether the task has data on the same machine. It has to also schedule, when you shuffle to decide which key values get on what machine. That can be done with hashes or with sorting intervals. It has to monitor the machines because it has to detect if one of the task trackers might have crashed, and then the map task there will not be completed, right? Now, if a map task is crashed or not completed, that's not a big deal. Then you ask another machine to take it over, right? But it has to take care of that. By the way, if a reduce task crashes, that is more problematic because then you might need to recompute things. So in the worst case, you have to start the job all over again from the beginning. But anyway, the job tracker has to worry about all of that. It also has to take care of the life cycle of the job, so the orchestration of map, shuffle, reduce, and so on, and the fault tolerance. So that's a lot of things for a single process to do. And because of that, we have scalability issues. So with the first version of MapReduce, we were able to scale it to 4,000 nodes. It's already a lot, but that's still a limit. And 40,000 tasks. And you see here the ratio is roughly 10, right? That's in line in what I said, that typically you have a multiple of the tasks are a multiple of the number of nodes, that times 10x. The other issue is that it's a bottleneck because there can be thousands of machines, and then the job tracker is there all by itself, taking care of all of that. So that's a bottleneck. When you start adding more and more machines, at some point that becomes too much. Another one is that, as we say, jack of all trades, master of none, right? It does too many things, so it cannot do any of them perfectly. And in particular, scheduling and monitoring are completely different tasks, but it's doing the two at the same time. It would be nice if we could separate them. Another issue that I mentioned last time is that because in the version 1 of MapReduce, you decide in advance which slots do mapping and which slots do reducing. During the map phase, the reduce slots are idle. They have absolutely nothing to do except waiting until the reduce phase is going to start or until the shuffling starts. And then in the reduce phase, the map slots have nothing to do anymore, except if something fails, then they would have to recompute, right? But it's all static. So that's a problem. It's an inefficient use of resources there. Who agrees on the problem? Who gets that this is problematic? Okay. And there comes the solution, yarn. So you know that whenever something starts with YA, it means yet another, right? So YAML, yet another markup language. And yarn means yet another resource negotiator. right? So this is what it means. It's basically a solution to these problems. But what's really nice is that it's a solution that is not specific to MapReduce. It's actually a very general way of solving this problem. And then we'll see it can be used for Spark, for HPC applications and so on. So it's very useful. So this is the architecture of Yarn. First, the centralized architecture shouldn't surprise you. It's exactly the same thing, you know, with name node and data nodes, HMaster and region servers, job tracker and task trackers. So here's a 4-pair to learn: resource manager, node manager, right? That's the name of the processes. So this is how Yarn works. But there is a third thing. These are the containers that you see here on the machines. So the containers can be seen as resource allocations. Each container has a number of CPU cores and some available memory, and it's kind of a virtualization of the resources, right? So you basically can allocate containers on every machine, right? So I'm going to explain very quickly how it works, not in the details, because I could otherwise spend a whole lecture, but that's not my goal here. I just want to explain on the high level how this is working, right? So that's Yarn. And what happens is that with Yarn, a client is going to connect to the cluster with a job. That could be a MapReduce job, but that could also be a Spark job or whatever, just a job. The resource manager is going to acknowledge the receipt of the job, but it's not going to take care of running it. Instead, it's going to delegate. So it's going to delegate and ask a container to do it instead. So it basically takes a container somewhere in the cluster and promotes it to an application master for that job. And so that application master is going to take care of the whole job, right? So it's going to request more containers. So the application master is going to say, hey, I cannot do it on my own. I need other people to help me. And so other containers to help. So it's going to request some more containers from the resource manager, who is going to grant them. And then you can forget that. So if you virtualize, you basically have the same structure with a job tracker, task tracker, but now it's all in the containers. So you have the application master, and then the containers that do the mapping and the reducing. For whom is that clear? Very good. So what happened is that we split the responsibilities. The node over there called resource manager is still responsible for allocating the machines, but it's no longer responsible for taking care of running the job. It's been delegated to a container. And now you have to imagine that typically when you have a data center like that, it belongs to a company. You're not the only one in the cluster. There might be 10 other people who are using the same cluster. It might be that there are 10 jobs running at the same time in the cluster. It means that there might be 10 application masters. So it means that it scales, right? You can have multiple people having jobs at the same time, and it's nicely going to be delegated to application masters. So we made the coordinator node a little bit more lightweight, right? What's very important to keep in mind, because this is a common misconception, I mean, you hear sometimes people that are blaming Spark for being slow or MapReduce for being slow and so on. But these frameworks here, like Yarn, they're not here to optimize performance. They are here to optimize the use of the resources in the cluster in a company with people competing for resources. This is what it's for. So its goal is to allocate the resources across multiple teams and people in a way that the cluster is fully used, so that there is no waste of resources. Okay, and so now we have this mini job tracker, task tracker thing that now is just done in containers, and the application master is orchestrating the whole MapReduce job. Some of the containers will do mapping, some of the containers will do reducing. What's also nice is that during the map phase, you don't need to pre-allocate reducing slots. You can do it dynamically when the shuffle begins. So you don't need to put resources idle waiting to reduce. For whom does that make sense? Right. So that is an improvement. That is an improvement. So it means that during the map phase, the machines you don't need can be used by other people in the company for doing other things, right? And then when you need them upon shuffling, you can request them. All right, then these containers, what do they actually stand for? So typically, I'm not a hardware person. There's plenty of people at ETH who are specialists in hardware. As a database person, I just know vague things about hardware. I know that there's some memory somewhere where the data is kept in order to work on. There's some CPU, or also called compute, that does the job. There is some disk that is storing the data in the long term and that I have to read from. And there is some network that is allowing me to send data across machines. I can say that I want gigabytes of memory. I want a specific number of cores. I want a specific capacity on disk or a specific bandwidth to read the data on the network. I can have a specific bandwidth. And all of that together gives you a container, right? A container is really the idea of specifying how much memory, how much compute, how much disk, how much network, and so on. Now, the disk and the network are a bit work in progress. They probably made a lot of progress on that, but traditionally, the resources focus on the use of memory and compute, so memory and CPU, right? Okay. So you have to imagine all these containers here. Think of them as an amount of memory and a number of cores. Yes?
The difference between container and the previous schema, or how would you call it? With,
Version 1.
Yeah, is a container additionally has allocates also some resources. It's not only a process or something like that.
That is the main difference indeed. So the difference with the previous version is that you only need to reserve the containers that you actually use. You don't have at the beginning to reserve all the resources you need and to keep the reduce part idle before the shuffling begins. Now, all you need to do is ask for the containers for mapping purposes. And when you're done, you can request dynamically the containers for the reduce phase, but you're no longer wasting resources. The other aspect is that you can also ask for more containers. If you realize there's some who crashed, you can ask more containers that intervene and take over. That's something you could not do in version 1 of MapReduce, right? But the idea that there's map slots and reduce slots is still the same. It's just that now the map slots and reduce slots are running on this kind of virtualized environment, the containers, instead of running directly as processes on the nodes, right? So this is the idea here. You could see it as a form of virtualization of the whole thing. Does it make sense?
So the containers allow to change the job that the real machine is running. It's we couldn't do that with a process before. Just
okay. So let me define what a container is, maybe for more clarity. The containers are basically like Santa Claus. They don't exist, or it's like Bitcoin. You know, it's there. It only has value because we think it has value. So the containers are really just something that is agreed upon, right? So the containers are just here because the nodes in the cluster agree that the containers exist. But really, what a container means when you request a container from the resource manager, you're basically really just asking for the authorization to have the exclusive use of, let's say, 10 gigabytes of memory and 3 CPU cores, let's say. But you probably will agree that this exclusive use of this amount of memory and of this CPU is only going to work if everybody else in the cluster respects that, right? And so what happens is that the node manager is going to declare to the resource manager, okay, I have 16 cores and I have 128 gigabytes of memory. And then what's going to happen is that the resource manager is going to say, of these 16 cores, I'm going to put 3 cores for this job that requested 3 of them, 5 other cores for that other job, and so on. And basically, when the execution happens, then the application master connects to the container and runs the process in there. And basically, because of the way that this is programmed, what is going to run is going to actually respect the allocated CPU cores and the memory allocation. But the containers, again, do not exist. It's really just something that people agree with. Like they have an agreement that I have received the rights for exclusive use of this number of cores and that amount of memory. Right. This is all done with tokens. I might not say a lot about that, but basically when you make a request, you get a token from the resource manager. Then you go to the node manager with a token saying, I was authorized to use this and that many resources. And then the node manager agrees to grant them to you.
So maybe before we didn't use containers. So the situation was like they were also running multiple processes on the machines, but it would be just multitasking managed by the operating system of the node. So everybody would take like as much as the operating system grants. And now the processes behave kind of like nicely that they use the agreed upon amount.
Yes, exactly. So that's really the idea that in version 1, you just get the whole machine. Like the whole node, the whole machine belongs to you, and you just take a map slot or reduce slot. And the difference now is it's like between buying and renting, right? Instead of buying the machine and just keeping it forever, you rent it for the time that you need it. And when you don't need it anymore, you just release it. Right? You can see it as some sort of hotel, right? And these are hotel rooms as opposed to a home.
Okay, thank you.
Right. Another question over there, I think.
I'm not sure I understand the advantage of putting the application master on one of the nodes that's also hosting containers as opposed to having it in a centralized position. Like I understand that you're able to break away the responsibility for creating nodes away from the one that's actually controlling them. But for instance, if you're thinking about your network topology, now you have a situation in which a lot of these individual task nodes are going to be communicating with each other, and that might increase the amount of bandwidth on the network. So I guess, what advantage does this give us vis-a-vis just like having the application master or all the application masters live in a centralized node?
I think this is the main advantage. It's really, again, the idea that you're not the only one using the cluster, and there might be 10 or 20 or 100 other people who are using the same cluster. And so if all of the job trackers or for the jobs were all on the main machine, on the coordinator node, that would be too much. So now that basically allows you to share the cluster with other people. This is what it gives you. Like instead of having the whole cluster to yourself and so on, you can share it with other people.
All right, thanks.
Oh, sorry. I could maybe add that in a way, you could consider that it's not that different in the sense that in the old version, you could consider that you have a cluster of 1,000 machines, and then Alice uses 100 of the machines and installs a name node on one of them, and Bob uses another 200 machines and installs another name node and job tracker on top of them. But this is more static. This is like done in advance. I give you the machines and they're yours, right? Now, what really is new here is the dynamic form of it. The fact that you just reserve and release these containers on the fly. You release them when you no longer need them, and you book them only when you need them, right? This is the idea. Okay. Let me move on. Note that I'm not getting too much in the details of that. So I used to cover it much more deeply in previous years, but we focus a bit less on this now. So now we have the resource management on that one machine for the entire cluster, the thousands of nodes, and then we have the application masters that take care of all the people running their jobs on the cluster. So one application master per job. So these sort of things shouldn't surprise you, that the node managers have these heartbeats that report that they are still here to the resource manager so that it can keep track of all the resources available on the network. So by now, this shouldn't surprise you anymore, right? And the resource manager knows exactly what node managers are alive, how much memory they have, how many CPU cores they have. The resource manager couldn't care less about monitoring the tasks. Once it has delegated to the application master, it's done, right? So it doesn't restart anything if it fails. That is also the job of the application masters to do that, right? Okay, the application master is application specific. You could have 2 people running MapReduce job, 3 more running Spark jobs, maybe 4 more running HPC meteorology tasks. It doesn't need to be it's not specific to anything. It's totally general. Like an application master can run whatever code you want in there. And the application master should, but of course depends on the code you put in there, it is supposed to monitor the containers that it got and to relaunch the containers that failed and book other containers. Now there's all kind of queuings. Again, I'm just waving my hands here and going quickly over that. When you allocate the resources in the cluster, so when people request containers for running job, you have multiple strategies. So one is FIFO, first in, first out. So you could say I'm giving the whole cluster to Alice. And when she's done, I'm giving the whole cluster to Bob and so on. That's called FIFO. Then you can have queues. So for example, if you have a company with a hierarchy, you can have in the executive meetings the decision on who gets what, maybe because of financing. And then you could agree, for example, that the math department is getting 40% of the resources and so on. So that's called a hierarchical queue. And this is really something that is decided by humans, like who gets what, right? And this is a target of the use of the cluster. And then what you can do is allocate capacity based on that. Like if you have a cluster of 1,000 machines and the math department is using, I don't know, 40%, then they get 400 machines. And the computer science department might get 600. And then you have a separate queue. You have a queue for the math departments and a queue for the CS department, for example, right? So this is then called capacity scheduler. And then you have what's called the fair scheduler, which is even smarter. The fair scheduler is able to notice that when the math department isn't using its machines because people are too busy writing on blackboards, then it can redistribute the machines to the computer science department. And if some mathematicians come back and want machines, it can preempt them and give them back, right? So this is then even more flexibly using the resources, right? Again, I'm not telling you any details, just a high-level view. One other thing that is extremely clever, and that was a paper written by I think between Stanford and Berkeley. So they moved a little bit between universities, but this is basically the same people involved in Spark. When you allocate a cluster, when you compute a percentage, it's easy if you just look at memory or you just look at CPU cores or you look at number of machines. You have only one dimension, right? So if you have a 10 cores and I get 40% of that, then I get 4. But the problem is when people have requirements, both in terms of memory and in terms of cores. So imagine that Alice is running a MapReduce job and she asks for plenty of containers, and each container is supposed to have 30 gigabytes and 2 cores. Bob is running some meteorology predictions, and he needs containers that have 10 gigabytes and 6 cores. So Bob wants more cores in the containers and a bit less memory than Alice. But then is the question, how do you allocate that fairly? How can you do that algorithmically? And these people manage to use game theory in order to come up with a measure such a way that you have no incentive to cheat on lying about the resources you need. And the trick they use is that they look for the requested memory and cores. They basically look at the percentage of the cluster. So each container here needs 3% of the memory of the cluster, 3% of that. 2 cores is 2% of that. 10 gigabytes, that's 1% of that. And 6 cores is 6% of that. And then you look at what's called the dominant resource. In the case of Alice, it's the memory that dominates. She's heavy on memory. She needs 3% of the memory. Bob is heavy on the CPU. The memory is insignificant for him. It's really the CPU. So that's what happens is that based on that, you see 6% here, 3% here. It means that the containers of Bob, based on that idea, are twice as large as Alice's containers, right? Because of 6 versus 3. And that means that when you allocate the machine, if, for example, they agree to have half of the cluster, then it would be fair to give Alice twice as many containers as to Bob because of this 3 versus 6, right? Who agrees with that? It's just a high-level thinking, but it's optimal game theoretically. And there is a paper called Dominant Resource Fairness. It's actually interesting to read. Yeah. So that's the idea. So in that case, for example, we could give 20 containers to Alice and 10 to Bob. And you see here you have 60%. Oh, I'm apparating and disapparating here somehow. Anyway, 60% CPU, 60% memory. So it's kind of fair. All right. So yeah, that's concluding it. Basically, you can use the yarn for MapReduce. You can use it for Spark, which we will see is based on DAG, distributed processing, directly acyclic graphs. You have the message parsing interface also that's quite popular, graph processing, and plenty of other uses. So it's fully general. And now you just run your MapReduce job in containers in Yarn rather than directly with job trackers and task trackers. So now we separate cleanly between scheduling and monitoring. We scale up. Now we can achieve more. I think it's 10,000 nodes and 100,000 tasks. We can be more available also because we share the cluster with other people. That's called multi-tenancy. Can have plenty of people using the cluster at the same time. So that is Yarn. And that was much, much shorter than what I did in previous years, because that's actually, it gets quickly complex. In fact, we realized that there's not much publicly available in documentation on what is done. So if as soon as you try to dig into it, you realize it quickly gets very complex. And so I decided instead to focus more on the MapReduce, Spark, like go more into the details of these rather than spending time on resource management, right? So you basically got less, just 25 minutes of Yarn instead of 3 or 4 hours. All right, so that brings us to Spark, Apache Spark. Any question on Yarn? No, Zoom? Okay, then let's go to Spark. So Spark is the next generation MapReduce. In MapReduce, what we do is basically we do something in parallel, we shuffle, and then we do something else in parallel, right? Technically, that's called reduce. But if you think of it, it's pretty much the same thing. It's really just about being in parallel. So it's parallel shuffling, parallel shuffling, parallel shuffling. So on the high level, this is MapReduce. But the problem of MapReduce is that you only shuffle once in a MapReduce job. You map, you shuffle, you reduce, and you're done. If you need something more complex, then you need multiple MapReduce jobs. And in fact, you end up having to have 10 MapReduce jobs to implement a specific algorithm, right? So it can be become very inconvenient at some point. So it would be nice if we could generalize that in a little bit and not constrain to just one shuffling. On the high level, if you look at it now in terms of data or data flow, you have an input followed by a map, which is applying a map function to the key value pairs. Then you have the intermediate data, and then the reduce that we'll call a transformation, and then the outputs. What if, instead of just having this, like input, intermediate, output, what if we have any directed acyclic graph known as DAG, right? Who heard of DAGs? Very good, all of you, all right. So directed acyclic graphs. So now we allow these values or key value pairs, but in fact, we'll see they don't even need to be key values, can be any values. They can be derived from each other via MapReduce, like all these things, in a fully generic way. The only constraint I have is no directed cycles. It sounds fair, right? You don't want directed cycles because otherwise you wouldn't be able to derive the data. So it cannot have cycles, but we accept any directed acyclic graph. That is the first thing that Spark supports as opposed to MapReduce. So this is what I call DAG query processing, right? So we have a name for what is now no longer a collection of key value pairs, but instead it's called the Resilience Distributed Data Set, or RDD. RDD, I'm going to say 1,000 times. RDD, RDD, RDD. So at the end, you will know that by heart, but it really means Resilient Distributed Data Sets. What is a resilient distributed data set? It's just a big collection of values, or big collection of items, if you want to call them items. A big collection of whatever. And it doesn't need to be key values. It can be key values, but it doesn't need to be key values, right? It's just a big collection. Furthermore, that collection is partitioned or sharded, or you can use whatever word you want, right? Shards, partitions, blocks, splits, whatever. But basically it's partitions. That's what the D for distributed actually means. So it's partitioned all over, and each one of the partition might be on a different machine. So you might have a cluster, and this is on one machine, this is on another machine, this is another machine, and so on, right? So it's partitions all over the cluster. Which is, by the way, also the case for the key values in MapReduce, right? It's also a partition, but it's just now it's more general. So now, these RDDs, they have a life just like water, right? It rains and then it evaporates again and so on. So here, an RDD is brought to life with a creation. Creation means you read a file from HDFS, you take some lists that a Python list, for example, that you turn into an RDD, and so on. So you create an RDD. Once you have an RDD, a first RDD, you can transform it. A transformation takes an RDD and returns another RDD, right? For example, we've seen transformations. That could be a map, that could be a reduce, and so on. These are kinds of transformations. But if I want to stay general, I don't need to specify what it does. It's just anything, any transformation that takes an RDD and returns another RDD, logically. And finally, we have what's called an action, which is when you're done transforming your RDDs in your DAG, because then the transformations, of course, are organized like this, right? At the end, so that was, let's say, the one you created, then you transform. You can even take 2 as inputs in a transformation, transform. Then you could take this and say, okay, that's my final output. I'm done. This is the data I'm interested in. What can you do with it? You can write it down to HDFS if it's petabytes of data. That's the first thing you can do, just like MapReduce. You can also print it on your screen. Maybe you know that it's actually very little. Maybe it's just 10 lines because it's very compact. So you can just download it and display it on your screen, right? So these are all the things that you can do here. You can also write it to your local file system if you prefer, if it's small enough. On S3 is another possibility, on HDFS, on Azure Blob Storage, like all of these layers that we've studied, or just on screen. And what I mean with on screen, for example, is on your Jupyter notebook, right? That is connected to a cluster. That works too. So creation, transformation, action. Yes, we have a question.
Said that the only constraint we have for the data flow is that it must be a DAG. Does that mean we could also have multiple RDDs as input, for example, because we have a kind of reverse tree structure or anything similar to that?
You can have absolutely multiple input RDDs. And in fact, imagine that you have a Python program. I'm going to show you how it looks like. When you have a Python program, you can write whatever code you want, right? So nobody would prevent you from creating an RDD from here. And then on the next line, you create another RDD from there. And then on the next line, you transform that RDD into another one. And then in the next line, you combine this one with this one. In fact, it's very common when you do it in the tutorials that you store your RDDs in variables. And you call them RDD1, RDD2, RDD3, RDD4. And basically, these RDDs, because of the way you build them, are in fact connecting through a DAG. Right? That's what it means. But indeed, it doesn't have to be a single input here. You could absolutely have multiple created RDDs. You can also have multiple output RDDs, and every time you have an action here and here. Okay, did it answer your question?
Yes, thank you.
Awesome. So creation, transformation, action. And so the creation, that would be the sources of the DAG. The actions could be the sinks. But in fact, you can have an action on anywhere, right? You could even say, after creating all of these RDDs, I could also ask to write that to HDFS. That's fine too, right? Doesn't need to be this one. I could also choose to also have this one printing on my screen or reading to HDFS. Okay. So basically, what we get is a DAG of RDDs. That's basically what we get when we actually do that. Now, the next thing is that when you create an RDD and you invoke a transformation to create other RDDs, and you look at what's happening on your cluster, like the CPU usage, the memory usage, you will be disappointed because nothing is actually going to happen. Nothing is complicated. It's lazy, it's computed. It's lazy evaluation. And the idea is that it's when you have an action, when you want to see it on your screen, then it's going to trigger all the computation in the cluster and create the RDDs to print it on your screen. So lazy evaluation. It's only when you have the action that it actually triggers an evaluation. There are exceptions to this rule. If you sort, for example, then when you create a transformation that sorts, it will actually also do a few computations. So there's a few exceptions. But as a rule of thumb, it's when you have an action that you trigger an evaluation. Okay. The implementation of Spark is actually done in Scala. You know that Scala and Java work on the same virtual machine, right? So it's the same ecosystem, but technically it's Scala. You can still use Java. You just have to live with a bit of a strange API. Looked from the Java perspective. Or Python works as well. You can use Python. It's just a bit slower if you use Python. You have to be ready for that. You can use it in the shell. You can use it in the Jupyter notebooks. So there's many ways, or you can write an application that orchestrates a job. Now, here's a concrete example. It's so much easier to understand concrete examples. I'll do it in Python, PySpark. So I told you, we like to store the RDDs in variables, and they don't have original names. You can call them whatever you want, of course, but you often see RDD1, RDD2, RDD3. So this is a creation where I create locally a list of values. Here it's boring, it's just 2 strings, but basically it's a local Python list on your clients, right? When you invoke parallelize, it's going to send that list to the cluster and distribute it, which I give you is totally ridiculous with just 2 values, but that's only an example, right? Typically you would have thousands or many more values than that. But basically, once you call parallelize, you create an RDD, and that's what the RDD would look like. I'm saying would look like and not looks like, because I told you it's lazy evaluation. When you do that, actually nothing happens. So this is why I put these dashed lines over here to basically say that it's virtually, this is what RDD1 corresponds to, but it's not evaluated yet. Then what happens is that we use RDD2 now with a transformation. So transformation, let's say we use a flat map. I'll show you examples of transformations. Flat map from RDD1 into RDD2. So RDD1.flatMap. And here I need a function. It's just like the map function or the reduce function, right? So the map function supplied to the map phase, the reduce function supplied to the reduce phase. And here you also need a function for the flat map. That function is supposed to associate a value, each one of the values to 0, 1 or more values. And here what we do is we tokenize. We just say, we cut it in 2 here, and we say this is the first value, the second value, and here this is the first value, the second value, right? So this is what my function does. Who heard about lambdas? Right? Lambda is just a way of creating a function as an object in a programming language, right? So it just says that this is a function that takes value as an input. It's an arbitrary name, and then it maps it to value.split, which creates multiple values. And what happens is that you get that virtually again, because again, it's lazy, so nothing happens yet. But in our minds, we can still anticipate that this is going to be split like this, and this is going to be split like this. It's a flat map, meaning that everything is flattened. At that point, you forgot that this was where it was separated. You forget that, you just see a flat list of 4 strings, 4 values. Who is with me? All right. And then we can display it in our Jupyter notebook. So now I say RDD2 count by value. It's an action. It's documented as an action. What's going to happen then is that the moment you press enter in your Jupyter notebook, the whole cluster sets into motion and is going to compute this, this, and this, and magically shows that in your Jupyter notebook. Right. For whom is that clear? Very good. So of course, flat map and count by value are just 2 of dozens of, I'm not going to say hundreds, I don't think it's hundreds, but at least dozens of examples of transformation. It's a restaurant menu, you have a huge menu to pick from, and I'm going to show a few transformations probably tomorrow, right? I can just show you a few today maybe, but we have 6 minutes left, so I still have time. So again, that's just a basic example, but any Spark job looks like that. You have creations, you have transformations, and then you have actions. In that case, printed on the screen, but you could also write it back to HDFS or wherever you want. So let's go through the menu now. So a transformation basically takes an RDD and outputs an RDD. We'll also see transformations that are binary, that can take multiple RDDs. Let's stick to one-to-one now. So this is an RDD, this is an RDD. Now, in order to make my examples a little bit visual, I'm going to model the values with shapes. So blue rectangles, that sort of thing. So the way you have to interpret that is that this is a value, this is a value, this is a value, this is a value, this is a value. instead of numbers and strings. I could also have, of course, use numbers and strings and so on, but I just thought it's more visual. Basically, you have an RDD, which is just a collection of values, which is mapped by a transformation to another RDD that is, again, a collection of values. At that point, this is logical. We are not talking about the implementation yet, right? I'm just saying logically, this is the collection we get. So here's a transformation that's called a filter. This transformation takes as input a function that says yes or no. So you feed the function with a value and it says yes or no. So what that transformation does is that it takes each value on the input, asks the function yes or no. If it's no, it just drops the value and doesn't forward it. And if it's yes, then it's forwarding it. So basically, you can see that the filter transformation outputs an RDD that is in fact a subset. I should even say a sublist, because the order is actually important, of this input, right? In fact, that closely resembles this selection that we did with MapReduce, right? It's just that in MapReduce, we needed to explicitly implement the filter. Here, there's already a built-in filter transformation that we can directly use. So RDD.filter, and then we pass a lambda that returns a Boolean given a value. For whom is that clear? Right? Very good. So that's one more difference with MapReduce. In MapReduce, we just have map and reduce. In Spark, we have 100 transformations to pick from a menu. Here's another one. It's called map. A map transformation takes one value from the input and outputs one value to the output, right? So that's what it does. A third one is flat map. Flat map needs a function that takes one value and it outputs 0, 1, or more output values in here. And because it's flat, you flatten again at the end. For whom is that clear? Who sees and agrees that what corresponds to the MapReduce map is not this, but it is the flat map? Who sees that? A few of you. Do you remember that when I explained the map function in MapReduce, I said the map function takes a key value pair and outputs 0, 1, or more key value pairs. I didn't say it outputs one key value pair. I said 0, 1, or more. So in fact, it's the flat map in Spark that corresponds to the map in MapReduce. So if you want to implement a MapReduce job in Spark, you would have to use the flat map for the mapping phase. Who sees it now? Very good. I should stop probably here. Do you have any questions on the material? Yes, over here.
All of this stuff, including the signature for like MapReduce, seems a lot more natural to express in a functional language like Haskell or OCaml. So why do it in Scala and Java and have to do .class and other messed up stuff?
That is an excellent question. That's exactly why, as I will explain in this lecture, Spark is still a physical layer. It's not the ultimate framework that you should use. It's good for engineers, but we will see that there's even better layers built on functional languages like JSONic, but it could be Haskell or something else that exactly provide a better user experience. So I fully agree with you. That was almost an announcement for the rest of the lecture, what you've just said.
Thank you.
All right. All right, so thank you everybody for attending today's lecture. I'll see you tomorrow at 9 a.m., even though we know that this is usually a lecture where people are not very focused, but I'll do my best to keep you focused on the big data lecture. Thank you very much, and see you tomorrow.